Hello, I'm testing out making a short video. So this is going to cover some of the stuff that I would have done in class for lecture note 16 about circuits, and specifically like how to draw circuit diagrams and how to interpret them, because that's hard to do in printed notes. So this is for lecture note 16, and it's sort of dispersed information that you can find in the chapter 21 of the textbook. So for now, we're going to have circuits that have three elements in them, three different kinds of things. The first kind of thing is a battery. We've already talked about batteries and what they do, but this is what they look like in a circuit. They're one or more pairs of alternating long and short lines. And the longer line is the positive end of the battery, and the shorter line is the negative end of the battery. And you might have sort of a pile of these, maybe 4 total lines or 6 total lines. And still the one with the long end is the positive end and the one with the short end is the negative end. And so this would correspond to something like a AA battery, with this being the positive end and this being the negative end. And like we talked about in class, a battery's job is to provide a constant voltage, which is a constant delta V. And so maybe this battery is 1.5 volts, or maybe it's 9 volts, or maybe it's whatever it says on the battery. It's some source of constant voltage. Then we talked about what happens when current flows through a material that's not a perfect conductor. We call that a resistor, and we draw that symbol as a squiggly zigzag line. That's supposed to represent that things are going to have a hard time flowing through it, I guess. And the resistor is labeled with its value R, its resistance, which is maybe some number of ohms. Maybe it's 82 ohms or something. That's the number I made up. It could be anything. So the squiggly line is supposed to tell you this is a resistor. It's something that lets current flow through. So it may have some current I flowing through it, but it's not going to do that for free. And what happens is when you have current flowing through a resistor, there's a voltage drop. So the delta V across the resistor, the voltage across the resistor is negative I times R, according to Ohm's law. And the negative sign comes if you're going in the direction of the current. That means that your potential has to be higher at the incoming end and lower at the outgoing end. And so if you're crossing the resistor with the flow of the current, your potential goes down. That matches one of the lecture exercises where we're talking about conservation of energy in resistors. So you lose potential energy going through the resistor, but you generate heat. The other thing that we will have in our circuits is wires. Wires are just lines. And we're going to model wires as perfect conductors so they can carry current, but that's all they do. And when you cross a perfectly conducting wire, you have delta V equals 0. Of course, wires aren't perfect conductors in the real world, but we're going to model them that way for purposes of this. So when you have a circuit, you're basically sticking together these symbols, which represent the connections that you're making between elements in the real world. And as we go on, we'll learn a couple of new symbols. We'll introduce a couple of new elements called capacitors and inductors, and maybe even other things as we go on, but this is enough to get us started. So when you're putting together a circuit diagram, you might have a place where you connect multiple wires together, and that's called a junction. And the simplest kind of junction looks like this. You have some wire, and you connect 2 different wires to it. Oops. And that right there, that dot is the junction. You don't have to draw a dot, it's implied, but that's where the junction is. And a junction's job is to distribute current around, or it lets current flow in different directions. And so you might have some amount of current I1 coming in, and then different amounts of current leaving through the two different wires. And there's one of Kirchhoff's laws is going to tell you what to do with those different currents, because they can't all three be different. They're all related to each other. And I just got an email. I don't know if you can hear that through the recording or not. Okay. Finally, every circuit is going to have at least one loop, and that's because you need a closed path for your current to flow in. You can't just have current go from one place to another. It has to come back to where it started. And so a simple example of a loop might be, let's put in a battery and some wire and a resistor, and I have to have at least one loop. And so I'm going to connect it back to the negative terminal of the battery. And that's an example of a loop. You can think about going around a loop in whatever direction you like, but I like to go the direction that the current is going, which is going to be from positive to negative. You can also start at any point on the loop. When you're writing down Kirchhoff's loop law, you need to traverse a whole loop. And so maybe you start here and you cross the battery and your potential goes up. You cross this wire and nothing happens, and you cross the resistor and your potential goes down, and you go back to the starting point, and that's how you will calculate a loop law. There's also different ways to connect elements in a circuit. So one way is series, and that just means, first one and then the other. And so there's some relationship between the currents through those two elements. And parallel means that the currents are able to flow through the two elements side by side, i.e. they're in parallel. And in that case, there's some relationship between the voltages, the potential differences across those two elements. So those are things that you should think about in answering the lecture note questions. Okay, that's it for this short video. Hope it's helpful.